Now we're going to take a look at an example. And so, as always, I would recommend that you try to work this example by yourself and then come back to the video to see the solution. So, as you're going through this example or as you're watching me go through it, I would also recommend that you have the rules pulled up from the notes that we just went over in the previous video. So what we want to do in this video is we want to sketch the root locus and any relevant asymptotes, and we're told that it's a unity feedback system with a forward transfer function given by g of s is equal to k divided by s plus 2 times s plus 4 times s plus 6. And so looking at this, we can note a few things. Of course, again, because we have unity feedback, we know that our h of s is just equal to 1. And so what that means is that our h of s times g of s, which is what we're considering for our open loop transfer function, is just equal to our g of s in this case. And so with that in mind, we can say that this open loop transfer function has 3 poles. And where are those 3 poles at? Well, we have one at s equals -2, one at s equals -4, and one at s equals -6. And so as we talked about before, we know that every pole is going to have a 0 as long as we're considering infinite zeros and infinite poles. So what this tells us is we're going to have 3 infinite zeros. So 3 infinite zeros, or 3 zeros at infinity, however you want to say that. And again, that's just because we have to have the same number of zeros and poles. So let's go ahead, and because we're dealing with, we know we have infinite zeros, we know we're going to need our asymptotes. So because of this, we need to define our asymptotes. So let's go ahead and calculate that even before we begin sketching out our root locus. So we need 2 pieces of information. The first is our real axis intercept, sigma sub a. And so what we're going to do is, remember, we're going to have a fraction here. So in the numerator, we're going to have the sum of our poles, so -2 plus -4 plus -6, and I've just written that as -4 and -6, minus the sum of our zeros, or sorry, I should say sum of our finite zeros, which in this case we don't have any in the numerator here, so that's just 0. And then in the denominator, we have the number of poles, number of finite poles, which is 3, minus the number of finite zeros, which again is 0. And so if we plug that in, we get that that's -4. Okay, so now for our theta sub a, this is going to be 2k plus 1 times pi divided by the number of finite poles, which is 3, minus the number of finite zeros, which is 0. And so remember that k value is going to be 0, 1, 2, and so on. And so what we can see is for k equals 0, that's going to give us an angle of pi thirds. For k equals 1, that's going to give us an angle of pi. And for k equals 2, that's going to give us an angle of 5 pi thirds. As we keep incrementing k, what we're going to see is we get the same angles. It's just going to be sort of plus 2 pi, or plus 360 degrees. So let's just go ahead and say higher k just results in the same angles. And so again, I know this choice of k that the book uses is lowercase k, and so that's different from our gain k in our g of s up here. So again, these 3 sort of asymptotes in this case are going to correspond to our infinite zeros. So we have 1 for each infinite zero. Okay. So now we're ready to start sketching our root locus. So let me go ahead and put sort of the startings of our plot here. So let's mark a few things. We said we had 3 finite poles. And so remember, we mark poles on our root locus with x's, so let's do that in green. So we had 1 pole at -2, we had 1 pole at -4, and we had 1 pole at -6. And then our 3 infinite zeros means we're going to have our 3 asymptotes as well. So let's add those in red. And so our point where those asymptotes intersect the real axis is at -4. So we can come here to -4. Let's make that a little bit smaller. And so at -4, an angle of pi thirds is going to be something like this roughly. So we have one asymptote here. We also have one asymptote at pi, so that's going to be in this direction. And then we have one asymptote at 5 pi thirds, which is the same as -pi thirds. So we have something that looks like that. And so again, that's essentially just dividing that 360 into 3 equal angles. All right, so now let's consider all of our rules as we sketch our root locus. So our first rule says that the number of branches has to equal the number of our closed loop poles. So in this case, we would have 3 closed loop poles, so we're going to have 3 branches. So let me just sort of write that over here as sort of what we're expecting. So we're expecting 3 branches. So our second rule says that we have to have symmetry about our real axis. So whatever we do has to be symmetrical about that sigma axis right there. And so we'll kind of check that as we go along. Our third rule is saying where our root locus can be on the real axis. So it said we have to be to the left of an odd number of our finite open loop poles and or finite open loop zeros. In this case, we only have finite open loop poles. And again, we're considering the poles of our open loop transfer function. So this h of s, g of s, and we said there are 3 of them at these locations. And again, for this rule 3, we're only considering those open loop poles and zeros that are on the real axis. So in this case, in this region here, we're on the real axis because we're to the left of 1 open loop finite pole. We are not on the real axis here because that is to the left of 2 finite open loop poles, 1 and 2. Once we move past that third pole, so here we're back on that real axis, so everywhere to the left of that, our root locus is going to be on the real axis because again, now we're to the left of an odd number, 1, 2, 3 of finite closed loop poles. Okay, so that's our rule 3 applied. So now for our fourth rule, we're saying we start at our poles, finite and infinite, and we end at our zeros, again, finite and infinite. In this case, we don't have any finite zeros, so we're just going to be approaching those 3 asymptotes. And so for the case of this sort of path over here on the left, or this branch on the left, that's just going to be moving to the left as our gain increases. So of course that one is sort of right on top of that asymptote. And for the case of these other 2 poles, what we're going to have is they're going to be moving towards each other like this. And at some point in between those 2 poles, we're going to have a breakaway point, and one branch or one path is going to come up and approach this asymptote. So it's going to be moving in this direction. And the other one is going to be coming down and approaching this asymptote. And let me see if I can do a little bit better job of making that symmetrical. So keeping in mind, of course, that this should be symmetrical about the real axis, we get something that looks like this. And so as we said, we of course have 3 branches. So one in this direction, one in this direction, and one here. So we have the 3 branches that we initially knew that we needed. So I lost my arrow there. And so again, keep in mind that these arrows are indicating the direction that our closed loop poles are moving as our gain is increasing. So direction of our closed loop poles as our k is increasing. And so in this case, we're talking about our gain k, which is this up here in our g of s. So hopefully after looking at this example, those simple rules make a little bit more sense in terms of how we apply them. But of course, that's going to get more comfortable and more familiar as we work through more examples. In the following videos, what we're going to do is we're going to figure out how we can refine this a little bit. So for example, one easy way we can see how to refine this is what exactly is this point? So where exactly do we break away? We know it's somewhere between -2 and -4, but we don't know exactly where. Another thing of interest is going to be where does this root locus cross over into the right half plane? And of course that is of interest because we want to see how long our system is going to be stable before it moves into the right half plane and becomes unstable.